Greetings. Once again, we are continuing with our discussions. Last time we talked about heat pump, refrigerators, and we are now continuing with reversed Carnot cycle. And now look at the performance criteria. Reversed Carnot cycle, performance criteria. If you remember Carnot cycle, we had said that Carnot cycle, if we talk of reversible processes, in the temperature, in the pressure volume domain, at process 1 to 2, 3, 4, clockwise. This was isothermal expansion. This was adiabatic expansion. And this was isothermal compression, and that was adiabatic compression. So if you remember, that was Carnot cycle. So we can have the reverse Carnot cycle, but let's have it in the temperature. In the temperature entropy axis, we'll have our one, 2, 3, 4. And so we are moving the direction 1 to 2, 2 to 3, 3 to 4, 4 to 1. And so in this reverse cycle, step 1 to 2, remember, step 1 to 2 is a case of isentropic compression. This was isentropic compression. Step 1 to 2 is isentropic compression. And so at that particular point, remember, we are coming from some low pressure and low temperature coordinate to high pressure, high temperature coordinate. From low pressure, low temperature, to high pressure, high temperature. Let's call the high temperature TA, low temperature TB. And so from step 1 to 2, we have that isentropic compression, and 2 to 3, we have that condensation. We have condensation and at constant pressure. Constant pressure. And step 3 to 4, this reversed Carnot cycle. Step 3 to 4, we have adiabatic expansion. We have adiabatic expansion. And of course, finally, we go back to the low pressure temperature state. We are back to state 4, and we have 4 to 1 is an evaporation. Step 4 to 1. Of evaporation. Now, we can depict this in a much more systematic and organized manner. That is, if we look at the steps in a much more systematic and more explorable manner, where you understand, we have, in this particular case, we have state 1, we have state 1, so this state 1, we have compression, and of course, it's going to state 2, step 1 to 2, we have compression 1 to 2, and that's negative work. Remember from our earlier discussions, it's negative work. And then we have here where we have our condenser. This is our condenser. And of course, we're releasing it 2 to 3. And this step, remember, 3 to 4 was adiabatic expansion. Force adiabatic expansion, so we have positive work. Adiabatic expansion, and of course, we have the evaporator. So we have this cold space, evaporator here. We're extracting as much heat as we can from the cold space as Q4. Now, in terms of efficiency, remember, in terms of performance, we normally talk of the ratio of the output over input. Talk about the ratio of output over input. About the ratio output over input. So that when we are talking about the coefficient of performance of this particular system, the coefficient of performance of this particular system, the coefficient of performance, the heat pump, this in this particular system will be Q to 3 over W. So W is the output. And so we are talking about Q to 3 over W for the heat pump. Remember HP, that's the heat pump. And we said this was a machine which can supply heat at high temperature. And remember, the refrigerator, we said, was a machine which will extract heat from a cold space. Don't forget that. Now, in terms of the coefficient, where Cp is the coefficient of performance. The coefficient of performance of the refrigerator will be minus Q41, remember from our drawings, Q41 over W. Why are we talking about W? W, remember, work is done on the fluid, not the fluid doing work. So it's negative. It's negative. Remember, we talked about the areas when we are talking of reversible processes. We are talking of the enclosed area in the clockwise direction, and in the reverse process, we are talking of enclosed area in the anti-clockwise direction. And so we put that negative because that work is done on the fluid will be negative, so that we have it as a positive quantity. So this W minus is to take the negative, is to take care of W being negative. So that is, we have a positive quantity. Now, if we continue with our discussion now, from first law, remember, talk of steady-state processes, we said that in this refrigeration cycle, we have flow processes, and each flow process is a component, and we said that for this particular components, the potential energy and kinetic energy at the entrance is about the same as the potential energy and kinetic energy at the exit. So there's basically no change. So that when we had that expression, remember, dH plus dCz squared over 2 plus gdz is equals to dq minus dw. Because that is kinetic energy, we are assuming it is 0. That change, we are assuming potential energy, that change is 0. Therefore, dH is basically dq minus dw. And being a state function, so we have q minus w is basically equals to 0. So that if we have the total value for q, therefore, based on this first law, remember that first law, based on that, so we have q for process 4 to 1 plus q process 2 to 3 minus w is equals to 0. And now, if we look at the coefficient of performance for these particular processes, so we have for q41, if we have q41 will be minus Cp ref for the refrigerator W, and this will be minus plus the other one for Q23. You just cross multiply. Q23 will be W, CP, HP, minus W is equals to 0. Of course, factorizing out W and dividing throughout by W, so you factorize W, and divide by W. Then we are going to have CP, HP minus CP F is equals to 1. Because that W, that will be minus 1, so when you take it the other side, it will be 1. So that CP, HP will be 1 plus CP F for the refrigeration. Now, if you look at the efficiency, for the heat pump, CP, HP, we saw that was Q to 3 over W. And if you look at that, that is the reciprocal of the efficiency for the reversible process, So that when we have in our system T, on that axis, temperature, and S, remember is entropy, T is temperature, remember S is entropy. The system which we have just drawn, 1, 2, 3, 4. That system which just drawn, we say that we have high temperature TA and TB, so that TA is greater than TB, it's high temperature, and we are saying that the reciprocal of this is basically the efficiency for the power cycle. So that, what are we saying? Therefore, the efficiency of CP, HP, when we are talking of the high temperatures being TA and TB within these two temperature limits, basically, therefore, will be TA over TA minus TB. Very important to note that this efficiency is basically the reciprocal for that, for the power cycle, the reversible one. And so basically the efficiency of CP in terms of the temperature between the temperature difference for this particular system, the hot temperature and low temperature, then it will be TA minus TA over TA minus TB. Remember, this corresponds to atmospheric temperature, and this is the temperature of the cold body, cold space. And so work is the area there. And so what are we saying here? So what we are saying is that therefore the coefficient of performance of the refrigeration cycle, therefore, the coefficient of performance every cycle plus, we had said was plus 1, was the same as, let me write it, the coefficient of performance, the heat pump, is the coefficient of performance, F plus 1. So if we take that expression for efficiency of the heat pump in terms of the high temperature, the low and high temperatures in that particular system, then we can substitute that there, so that TA over TA minus TB is equals to CP plus 1. And so we have TA over TA minus TB minus 1 is equals to CP F. And of course, if you take a common denominator, TA, TB, so that will be TA minus TA plus TB. And so that will definitely give you that this is TB over TA minus TB. And that will be the cycle performance for the ref cycle. Well, remember that is the refrigeration cycle. It is the heat pump.